Everyone has heard of the tides. They occur every day all over the world. There are high and low tides, spring and neap tides, which may not be that familiar but will be explained in this video. But first let's look at two examples. This one, in speeded up fashion, shows a tide coming in. Maybe you've been on a beach like this and have had to keep moving your towels and chairs back as the tide comes in, but certainly not as fast as this. At the root of tide behavior is the gravitational effects of the moon and sun on Earth. Let's start here with the Earth, surrounded by oceans for simplicity, and the moon. The moon has a gravitational attraction on the Earth, as indicated by this arrow. As a result, the oceans are somewhat pulled in the moon's direction. The solid is also pulled forward, but not as much because it is further from the moon. As you know, the force of gravity gets weaker with distance. The actual distance that Earth moves is only a few centimeters. And surprisingly, Earth is also stretched just a little bit, actually slightly deformed. The water can move much more because it is fluid. The oceans on the other side of the Earth are also pulled forward, but even less than that solid part of the Earth because they are even further from the moon. So we have a bulge of water on this side as well as the side facing the moon. You will also notice how the water depth got lower above and below on this picture. This picture shows that the moon's force on the near side is stronger than on the far side by about 6.8%. The bulges are high tides and the lower parts are low tides. As the Earth rotates, there are two high tides and two low tides. But at one given location, not shown here, you would see two high tides separated by about 12 hours, and then two low tides also about 12 hours apart. However, some places experience only one high and one low tide each day due to local geography. At coastal regions, it takes about 6 hours for the water to go from high to low or from low to high tide. Where does the water go when it goes out during low tide? Well, if it goes out in one region, it comes in at another region. Now let's bring the sun into the picture. It also acts on the Earth. This diagram is not to scale. The sun is much further away, so that its effect on the tides is almost half, 44%, of that of the moon's. Nevertheless, the sun's presence is important when it is lined up with the moon and Earth, because their gravitational effects will combine to make the largest tides. This happens at the new moon, where the high tides are higher and the low tides are lower. This highest tide is called a spring tide. The word spring here has nothing to do with the season. One origin is that it's either from Scandinavian or German, which in both cases means to jump up. But when the moon goes to its first quarter, the gravities pull in different directions, and the sun actually takes away from the moon's tidal effect. The high tides are not so high, and the low tides are not so low. This more moderate tide is called a neap tide. Again, the origin of this word is not clear. One idea is that it comes from an old Anglo-Saxon word meaning without power. Another source says it means low. At the full moon, the moon's and sun's gravity lined up again, so we get another spring tide. At the third quarter, the gravities are out of alignment again, so we get another neap tide. Then back to the new moon, and the moon's gravity combines with the sun's to start all over again with another spring tide. Only large bodies of water, namely oceans, are subject to these tides. The spring tides of the Great Lakes, for example, are less than 5 centimeters in height. Each month, while the moon goes around once, the Earth spins about 30 times. So 2 high tides a day gives 30 times 2 equals 60 high tides. However, the alignment of moon, earth, and sun occurs only 2 times, at new moon and full moon. So of those 60 high tides, only 2 are the higher spring tides. And by the same reasoning, there will only be 2 neap tides per month. The difference in height from low tide to high tide is called the tidal range. Here we can see the mean high tide, mean low tide, and the average sea level. The average tidal range in the open ocean is about 1.8 meters. Closer to the coast, this range can vary significantly from 0 to 12 meters. Larger bodies of water have higher ranges, and the geography can act as a funnel to amplify the range. The world's largest tidal range of 16.3 meters occurs in the Bay of Fundy. So this is how most sources explain the origin of tides. I would now like to give a more detailed explanation for those who are interested as to why the tides on the opposite sides of the Earth will be equal and in opposite directions. Here is the Earth before the moon is in the picture. I'm going to simplify the picture by representing the Earth by this line. This will be the ocean nearest the moon, and this will be the ocean on the other side of the Earth. So now we bring in the moon, and refer to this earlier picture in which the length of the 3 arrows represented the effect of the moon's gravity on the 3 parts of the Earth. Recall that the nearest ocean felt the strongest effect of the moon's gravity, so it moved the furthest. I will show the ocean having moved to here, and this arrow will represent the distance. The Earth felt less attraction, so it moved a bit less. And the far side was least attracted, so its distance will be shown like this. Now, what we want to know is, from the Earth's point of view, how far has each ocean moved, and in what direction? While we are standing on Earth, we can't see it move, but we can see the oceans move by their tides. So what we're going to do is take this distance that the Earth moved and subtract it from itself and the other distances as well. Doing this will show how much the oceans moved with respect to the Earth. If we now add the black and red arrows together by placing them on top of each other, we see that they are equal in length, but pointing in opposite directions. This means that they cancel each other out, which is what we want, because we can now say this is Earth in position 0. We now add the black and red arrows for this ocean, and you can see that there will be a net movement to the right, as shown by the green arrow. And the length of the arrow represents how much the movement was, so that will be the tide. If we do the same thing for the other ocean, you can see that the direction will be to the left, and the amount, that is the length of the green arrow, is the same as for the other ocean. I'll put Earth here like this, and now I'll remove these arrows since they canceled each other out. By the way, in physics, these arrows are called vectors, and combining them, as we just did, is called vector addition. I'll put the far ocean here and the near ocean here. Now I'll remove these arrows and these, and now combine it all together. A complete explanation of tides is quite complex and beyond the scope of this video and me, quite frankly, but this is a good approximation. Now let's consider some tidal confusions. For example, is a tide and a tsunami the same thing? They are often confused, but they are not related. The waves from a rising tide are the result of the gravitational effect of the moon on Earth. In a tsunami, a series of waves is caused by an underwater event such as earthquake, volcanic eruption, or a landslide. Here is an animation from the National Oceanic and Atmospheric Administration that shows how a tsunami starts with an underwater event and is swept onto the land. Rapidly receding water like this on the coast could be an indication of an impending tsunami. The damage, of course, is considerable, as this picture shows. Tidal bores. They occur along a coast where a river empties into the ocean. This white arrow shows the direction of the river, and the red arrow shows the tide as it's being funneled into the river against the river's current. Here is another tidal bore along the coast. How about surfing on a tidal bore? This clip shows 4 international surfers surfing in Moncton, New Brunswick in 2013 on the Petitcodiac River. This tidal bore results from the Bay of Fundy and occurs twice a day in downtown Moncton. A red tide is not a tide at all, but an algal bloom, which is an accumulation of algae or cyanobacteria that discolors the water. Here's another one. The bloom is in this green area. Lastly, riptides. These are not a tidal feature, but a strong ocean current running along the surface of the water. A riptide runs from the shore to the open ocean when tide water flows steadily out to sea. They can help surfers to get out to the sea without having to paddle, but they can also be dangerous to swimmers who can be swept out to sea. But rip currents are different. They are caused by the shape of the shoreline. This picture shows a well-defined rip current that must be avoided. Most are not so obvious. Here's an
Here's how a rip forms. When waves break on a beach, they push water towards the shoreline. Once that water reaches the shore, it has to find a way to get back out to sea. So it flows into the deeper channels and away from the shore. These deeper channels are called rip currents, or rips. These are the things to look for: deeper, dark-coloured water, fewer breaking waves, a rippled surface surrounded by smooth waters, anything floating out to sea, or foamy, discoloured, sandy water flowing out beyond the waves. Rips don't always show all of these signs at once. Some rips may only have 1 or 2 signs.
Here's a 3-point summary of the main ideas in the video. High tides on both sides of Earth are caused by the moon's gravity. The sun's alignment with the moon accounts for the spring and neap tides. And these are not true tides: tsunamis, red tides, rip tides, and rip currents. To end this video, let's have a look at another dramatic example of high tide in the Bay of Fundy.
This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water?